Good afternoon, everybody. Welcome to reinforcement learning session number 11. We're going to have 4 presentations, 2 20 minutes and 2 10 minutes presentation. The only note is after each talk, if you would like to ask any question, please go to the mics. The first presentation is Configurable Markov Decision Processes, and Alberto Metelli is presenting.
Hi, everyone. Thanks for the introduction. I'm Alberto Metelli. I will be presenting the Configurable Markov Decision Processes. This is a joint work with Mirko Mutti and Marcello Restelli. We are all from Politecnico di Milano. So let us start with some motivating examples. Consider, for instance, Formula 1 Grand Prix. Here we have an agent that is a driver that wants to minimize its lap time. So this agent is interacting with the environment in order to learn an optimal policy. But there is something more we can do to help the driver. For instance, the track engineers can configure the vehicle by changing the kind of tires or the wing setting so that the performance of the pilot can be improved more. Let us consider now another example. Here we have instead a student that is interacting with an online teaching platform. The goal of the student as an agent is to maximize the amount of information it learns during the course. However, there are different students, and different students have a different ability in the way they capture the information it is provided by the course. So the online platform should be configurable in the sense that it should be adaptive to the different skills and abilities of the students. Again, we have an agent, the student, and a part of the environment, which is the teaching platform, that can be configured to improve the overall performance. And finally, let us consider the design of a website. We might have different goals in this case. For instance, we might want that a possible surfer is induced to spend as much time as possible on our website, or it might be induced to traverse a set of links and get to a specific page and click on a banner. Again, we have an agent, the surfer, we have an environment, the website, and we can configure the environment by designing, for instance, the organization of the links and the graphical aspects. All those configuration activities have an effect on the transition probabilities and on the way the learning process for the agent goes on. So what is going on in all these examples? We still have an agent that is interacting with an environment. Such agent can be, for instance, the driver or the student or the surfer. And we have the environment, for instance, the car, the online teaching platform or the website, but differently from the classical Markov decision process, here we have a configurable environment so that we can act even partially on the environment in order to improve the final performance. How can we model this new kind of interaction? We introduce a new framework, the configurable Markov decision process, which is defined in a very similar way to the classical Markov decision process. We have basically the same ingredients, but we no longer have a transition model because the transition model is now configured, and so we have instead a model space that is the set of all environment configuration that we assume to be admissible. And symmetrically, we have a policy space, which is the set of all policies our agent can play So we have a new framework to model environment configurability, and we define a new learning problem. Now, what we want to do is basically to determine an optimal policy together with an optimal environment configuration so that the expected return is maximized. How can we solve such a learning problem? Well, in principle, we could adapt more or less any reinforcement learning algorithm to account for the environment configuration. However, configuring the environment is actually an activity that has to be performed with some attention. Think, for instance, to what would happen if we select a wrong configuration for a vehicle in a car race. For these reasons, we decided to resort to a safe learning algorithm, which is inspired to safe policy iteration that allows us to achieve some theoretical guarantees. Few words about safe policy iteration. It is a policy search algorithm that is based on the idea on optimizing a lower bound on the performance improvement instead of optimizing directly the expected return. This bound is made of two terms. The first one, the advantage term, which represents the promised performance improvement we achieve by moving the policy from pi to pi prime. This is a local information similar to the gradient, and so it is reliable as long as pi prime is close enough to pi. For this reason, this justifies the presence of the second term, which is a dissimilarity penalization that discourages choices of pi prime which are too far from pi. By the way, the idea of optimizing a lower bound of the performance improvement is at the basis of many successful recent reinforcement learning algorithms. How can we extend this bound to account for the environment configurability? Well, essentially, what we need to do is to add a new term, which is a model advantage term. So overall, we have the model advantage, which preserves a similar meaning, and it represents the local performance improvement obtained by moving the transition model from capital pi to capital pi prime under the fixed policy pi. Symmetrically, the policy advantage has a similar meaning. And finally, we have a joint dissimilarity penalization, which accounts for both the contribution of the model and that of the policy. Once we have this bound, we need to define pi prime and capital P prime in terms of P and pi to perform the update. Again, we adopt a similar approach to that of safe policy iteration. We define pi prime as a convex combination between pi and a target policy overline pi, which defines the update direction and symmetrically for the model. I'm going to talk about how to select the target model and policy in few slides. When we have this parameterization, we can easily determine the optimal coefficients alpha and beta by maximizing the previous lower bound, which turned out to be a quadratic programming problem. Notice that this approach that we called safe policy model iteration, SPMI for short, besides the monotonic performance improvement guarantee that it inherits from a safe policy iteration, it performs what we call a joint and adaptive optimization, in the sense that at each update step, possibly both the model and the policy are updated based on the lower bound that trade-offs between advantage and dissimilarity. One important point we need to discuss now is how to model the space of admissible environment configurations. The transition model, typically in many real-world cases, encodes parts of the environment which are configurable and parts of the environment which are not. Think, for instance, to the Formula One problem. In this case, it is reasonable to configure the car, but of course we cannot act on the physical laws governing the interactions between the car and the road, and both of them are part of the environment. So we need at least to consider two cases. We can model we can represent the model space as an unconstrained model space in which all models are valid, and this is, for instance, the case of the website. or we need to specify explicitly the dependence of the transition model on a set of parameters omega, and this is a suitable case to be used for instance, for the Formula 1 problem. A particularly convenient parameterization is when our model space can be seen as a convex hull of a set of vertex models, which is the case we are going to consider in this talk. Another point, as I anticipated before, is how to select the update direction both for the policy and for the model. Here we focus on the transition model. The update direction, a straightforward choice to select the update direction is to resort to the definition of a greedy model, which is similarly to the policy, the model that maximizes the advantage function. This choice, besides being the best local choice, has typically displays an oscillating behavior in the algorithm because sometimes the algorithm tends to switch continuously between one greedy model and another. In order to avoid this behavior, we can resort to a persistent target choice in which we keep our target fixed unless we find a greedy model which yields a better bound value. Essentially, the greedy approach is based on maximizing the advantage. The persistent is based on maximizing the bound almost. Let us go to the experimental evaluation. We evaluated our algorithm in two illustrative domains in order to show the benefits of the environment configuration, and we compared several approaches for learning both the policy and the model. The sequential approaches basically first perform the policy learning, followed by the model learning, or vice versa. The alternative approach instead forces one step of policy update followed by one step of model update. And finally, the adaptive approaches try to optimize either the policy, the model, or both based on the bound value. And here we have SPMI, which is the algorithm we presented so far, and SPMI SUP, which is basically the same algorithm using a more conservative lower bound. The domains we consider, the first domain we consider is the student-teacher domain. It is a simple abstraction of a student interacting with an online teacher, an automatic online teacher. Here, the teacher provides the student with a sequence of statements involving some literals, and the goal of the student is to assign values to literal so that such assignment is consistent with the statement. And the student is rewarded whenever the assignment is consistent. In order to model the fact that different students might have different abilities, we assume that the student can change only a limited number of literals at a time. So in these slides, we show the expected return as a function of the number of iterations of the considered algorithm. Let us focus on the plot on the left. Here, what we have basically, and focus on the convergence, on the performance at convergence, which is the performance we are able to achieve by both learning the policy and configuring the model. What we can see is that such performance is larger with respect to the performance we are able to obtain by just learning the policy, which corresponds to the black ballot SPI, and the performance we are able to achieve by just learning the model and keeping the original random policy, which corresponds to SMI and the purple ballot. The other environment, the second environment we considered is the racetrack simulator, which is a simplified version of a car racing problem. Again, here we have a driver that wants to minimize its lap time, and we have a track engineer which acts on the environment, and in particular, it can configure two dimensions of the vehicles, two features of the vehicle, which are the vehicle stability and the engine power. By changing the engine power, for instance, we are able to achieve higher speeds, but with a higher probability that the engine breaks, triggering the end of the episode. Here we show the coefficients of the vertex model. By the way, we are in a parametric model space, so we have different we have 2 dimensions, the vehicle stability and the engine power, so overall 4-vertex model. What we can see is basically that the adaptive algorithm, which are SPI and SPMI SUP, are able to learn the optimal configuration together with the optimal policy faster with respect to the alternated approach. One important point we should discuss now is whether we could model environment configurability using the existing methods. Well, we think that we cannot do that at least straightforwardly. For instance, we could think to include into the policy, into the agent policy, the activity of configuring the environment. However, in this way, we wouldn't be able to constrain the model space in a proper way. And by the way, we assume that the configuration activity occurs at the beginning of the episode. Moreover, when there is a supervisor like a track engineer in charge of the configuration activity, we could resort to a multi-agent system approach, but also in this way it would be quite misleading because actually there is no real interaction between the supervisor and the agent, as the supervisor is just acting at a higher level. To conclude, we presented a novel framework to model environment configurability, so the possibility to alter some environmental parameters. And on top of this framework, we provided a class of learning algorithm, of safe learning algorithms, which are able to exploit the interconnection between the policy and the model. And finally, an experimental evaluation, although preliminary, to show the benefits of environment configuration. The take-home message, I believe, of this work is that environment configuration and configuring the environment can be very beneficial for the agent performance. Indeed, by a suitably chosen configuration, we are able to achieve performances which are impossible in the original environment. We believe there is actually a lot of work to do in this field. In this work, we considered a linear parameterization for the transition model and the policy. We could think to extend the model to account for general dependence of vectors of parameters. And moreover, also in this work, we assumed that both the policy space and the model space are known. Clearly, in reality, this is not the case, at least for the configuration space. We could think how to infer the configuration space by the interaction with the environment. And I think I'm done. Thank you for your attention. By the way, you are all invited to our poster, number 88, tonight.
Any question? Okay. Okay. Go ahead, please.
Hi. Very interesting modeling framework. Did you consider slight variation where the model could be changed during the episode? Like, for example, for the car, you start boosted, and when the engine starts to show weakness, you switch back to a non-boosted configuration or things like that?
In this framework, we didn't consider that possibility, but I think it's very interesting because even within, it's much more fine. It's finer with respect to our framework, in which you can only configure your environment at the beginning of the episode, and in each episode you select the configuration you believe is the best one. But of course, it is an interesting extension, I think.
Maybe if I can fit one more question. How does this compare to multi-agent system where this environment configuration would be handled by another agent, for example?
Yeah, I think that for sure you can model this as a multi-agent system, but I think you are introducing some more complicated, let's say, structure that is not there. It's not, there is not this kind of structure here because basically, in a way, the supervisor is aware of the agent, but the agent might not be aware of the supervisor, and everything works the same way. Thank you.
Thanks.
Any other question? Okay, let's thank the speaker and move to the second talk. So the second talk of this session is beyond the one-step greedy approach in reinforcement learning, and Jonathan Efroni is presenting it.
Hello, everybody. Thank you for being here. Yeah, Facebook alerts. Sorry. Yes, so I will discuss today about the work I've done together with Gal Dalal, Bruna Scher, and Shai Manor, my supervisor. The title of this work is Beyond the One-Step Greedy Approach in Reinforcement Learning. Now, as you can probably guess, the name is this work is will deal with multiple-step look-ahead policies in reinforcement learning and how we can use them in a proper way. So a bit of a motivation. Now, multiple-step look-ahead policies had been with us for a while in reinforcement learning. They give state-of-the-art performance by combining Monte Carlo tree search or model predictive control, as some of the works that you've seen here, even today, into the general framework of reinforcement learning. We have here this neat explanation about MCTS by the survey by Brown, which says basically that Monte Carlo tree search involves iteratively building a search tree, and the best performing root action is returned, meaning that the action that we are doing in the root is basically an outcome of a multiple-step look-ahead policy. And probably the most famous example nowadays for a multiple-step look-ahead policy in RL is the AlphaGo Zero, that done a great job playing the Go game, as everybody knows probably. Now, although these class of policies have been with us for a while, formal understanding of how we can use them in a proper way still lacks. The question that we wish to ask here is how to integrate look-ahead policies into reinforcement learning and get the theoretical guarantee of convergence. So what this work will be about is basically to replace the one-step greedy policy in policy iteration with a multiple-step look-ahead policy and show we can prove convergence and analyze the properties of this algorithm. A bit of a recap now. So one-step greedy policy is at the heart of reinforcement learning. It's given in the form that we see here. And intuitively, you can think about it as the solution of this tree search problem with depth of 1. Or put it in another way, one-step greedy policy is a solution of a one-horizon decision problem. And it is central in policy iteration, as we shall see in the following talk, in this talk. And because it's central to policy iteration, it is also central to many other reinforcement learning algorithms that are based on policy iteration. And so our contributions here will be to define a multiple-step greedy policy and prove some of its properties. We'll give the corresponding policy iteration procedures, which we name age policy iteration, which uses the age greedy policy, and the kappa policy iteration, which uses the kappa greedy policy, pi kappa. And we've done also a sensitivity analysis, which we shall not discuss here, and you can obviously read it in the paper. As everybody deals with here, we will deal with the Markov decision process. We consider a gamma discounted MDP, as usual. We will use the notations we give here, and we will denote the conditional expectation of random variable x, given the starting state is S, by the expectation with a subscript of vertical line and S. It's going to be shorter. And the reward of the state at time t will be denoted by RT. It's basically the reward at time t. And the value of the state at time t is going to be denoted accordingly, meaning by VT. That's like the value of the state at time t. And the goal is the usual goal. Find the optimal policy, pi star. So we can do it using the usual policy iteration algorithm. Now, this algorithm is quite old. It was first given by Howard in 1960. And it basically involves in iteratively applying improvement and evaluation. In words, we can think about this algorithm as performing one-step greedy, as taking a one-step greedy action with respect to the current value, and then estimating the value of the policy. A recent advancement in our understanding of this algorithm showed that this algorithm actually converges after a polynomial number of iterations, as you can see here. And moreover, a major downside of this algorithm is the fact that it can be quite costly to evaluate the value of the policy, pi, especially if the discount factor gamma tends to 1, right? So a lot of people also tried to relax the evaluation stage by using partial evaluation. For example, the modified policy iteration algorithm basically uses the n-step return, which is much easier than the full evaluation task. And the lambda policy iteration algorithm uses the lambda return. So both of these basically do some form of partial evaluation, meaning they change the evaluation stage. However, and to the best of our knowledge, in all of the quoted works that we've seen here, nobody asked whether we can change the improvement stage, meaning to take something more complicated than the one-step greedy with respect to V. So we now ask, is the one-step greedy is the best choice for us? So our answer to this is no, and as a motivating example, we obviously know that TD0, which is some form of one-step way to do the evaluation task, is not optimal. We know that it is better to use some TD lambda and with some parameter lambda. So that's the reason that we wish to tackle it. In some sense, one can interpret the work that I will show to you now as generalizing the use of the n return and the lambda return to the improvement stage. Great, so that's a bit of a background and motivation. So let's start with what we have done. So we define the usual age return, which basically looks age steps ahead, and at the eighth time step, we get the value. We define here the age greedy policy with respect to V to be the solution of the following optimization problem. In words, in order to calculate the age greedy policy, we need to solve an age finite horizon MDP. And the age greedy policy is the first optimal policy of the sequence of age policies. And furthermore, one can see that for age equals 1, we recovered one-step greedy that we have earlier. And for age equals infinity, we get the optimal policy because the term, the value function there decays exponentially. Great. We can calculate it using standard dynamic programming approach, using forward research or approximate techniques. And intuitively, one should think about this policy as the solution of the following research problem with depth of age, where at the leaves we get the value and not the reward. Now, importantly, this type of greedy action has the monotonic improvement property, which also has been discussed here before me. So the age greedy policy with respect to V pi is monotonically better, or just better, if you want, than pi. Meaning, if we are in some state S and we would play the policy, the age greedy policy, with respect to V pi, we are sure to get larger reward than if we would play pi. Now, this property is really important. It's fundamental to any policy iteration method. And it also motivates us to define here the age policy iteration algorithm. The age policy iteration algorithm basically replaces the one-step greedy policy at the improvement stage with an age greedy policy. with respect to v. And we here also generalize the result that we've seen earlier. We see that the h policy iteration converges after a finite amount of iterations, where as age increases, we need less number of iterations. Now, this would seem intuitive, but obviously we should keep in mind that as age increases, each iteration is also more costly, right? Because we need to solve a decision problem with larger horizon. So generally speaking, with no other knowledge, there is no reason to choose a certain age over the other. And specifically, there is no reason to choose the one-step greedy, meaning age equals to 1. Now, at this point, we might like to ask whether we can define some greedy action with respect to all the age returns. Can we do that? We again start with defining the age return, as we had previously. And the kappa greedy action with respect to a value function v is defined as the kappa geometric weighted average of the age returns by this simple expression. Intuitively, also we can think about this kappa greedy policy as being optimal with respect to some probabilistic setting, in which the probability that we would need to solve a tree with a horizon of age has the geometric distribution of kappa. However, it might seem like unnatural to solve such optimization problem, but luckily we can write the kappa greedy policy, the optimization problem that we need to solve in order to get it, differently. We can write it in this form that we see here. Now, this form, I claim, is much more simple. We actually know how to do it. We basically need to solve a kappa gamma discounted Markov decision process with a shape reward, right? We can solve it by dynamic programming or approximately by Q-learning or any other RL algorithms that you can think of. And again, we have that kappa interpolates between the one-step greedy for kappa equals 0 and between the optimal policy for kappa equals 1. You see that the last term cancels out. It cancels out if we plug a kappa equals to 1. Yet again, we have the important improvement property, meaning the kappa greedy policy is better than pi, which leads us also to define the policy iteration procedure in which we replace the one-step greedy action with respect to v by a kappa greedy action with respect to v. And we also have similar in flavor theorem, which shows that this algorithm converges after a finite amount of iterations, which decays as kappa increases. And yet again, we have that as kappa increases, each iteration is going to be more costly. And again, there is no actual reason to prefer a certain kappa over the other, much like we had for the age policy iteration case. Now, we concluded on the theory side by showing that it is possible to combine kappa policy iteration with partial evaluation. Meaning we call this algorithm kappa lambda policy iteration. In this algorithm, we use in the improvement step the kappa greedy policy, and in the evaluation stage, we use the lambda return. We showed obviously that this algorithm converges to the optimal policy, but more importantly, we think that this algorithm emphasizes some delicate issue. That we have 2 degrees of freedom in an RL problem, in a control RL problem. One degree of freedom, lambda, which is known from the TD lambda algorithm, controls on the evaluation horizon, whereas kappa, which is a different degree of freedom, controls on the horizon of the control problem, which we wish to improve according to right now. So great. We concluded with a small toy problem. A toy planning problem. I want to emphasize that it's just a planning problem. It's an n by n grid world, and we have like a single goal and a small random reward on the rest of the state space. And we just tested the performance of H policy iteration and kappa policy iteration and how much time it took us until we converged to the optimal policy. And by saying performance, I mean the running time, meaning as the running time is lower, the algorithm is better. We got these following graphs, and we see that the lowest running time is obtained for some age value, which is intermediate, meaning not 1 and not infinity, and also a similar result for the kappa, meaning the optimal kappa value is also intermediate, between 0 to 1. And the conclusion is obviously that it can be beneficial to consider multiple-step greedy policies here. And just as a recap, again, this is policy iteration. And the rest of the points that we see here are the generalizations that we saw in this talk. So to conclude, and the take-home message should be that reinforcement learning is coherent with bigger than one-step greedy improvement. And it can empirically also outperform the one-step greedy approach. Some questions for future work, which we find interesting, is obviously how to choose these parameters, kappa and age. Is there some property of the MDP that can guide us? Moreover, how to extend the algorithm that we saw here to the model-free and approximate reinforcement learning case. We also started to consider this direction in a recent archive publication. And the final and maybe more general question is, are there any other surrogate decision problems that we can define that will lead us to convergence to the optimal policy? So that's it, and we invite you to our poster. I will be there, and also Gal, Dalala. Thank you.
Question?
Hi, thanks for the talk. So in your kappa policy iteration, you're using the same policy for the whole rollout. But in the H policy iteration, your policy is essentially changing at each time step. And I was wondering if the theoretical result holds if you were to maintain the policy fix for the H rollout.
If I understood correctly, in each iteration of both the H and kappa policy iteration, we change the policy.
No, so what I meant in your equation for the H rollout, you have the argmax, and then inside that you have a max over pi 1, pi 2, pi 3, all the way to H. So if you were to just have the argmax pi and use that same policy for the rollout,
I see what you mean, yeah.
Would your results still hold?
So if you would take the argmax on the entire policy, you would get a non-stationary policy, right? Because you have like pi 0 up until pi h minus 1. And this algorithm is more like related to some other algorithm by Bruno Scherer, which is named non-stationary policy iteration. I think that the machinery will still work, but you would need to evaluate non-stationary policy, where here you evaluate a stationary policy.
Thanks.
Sure.
Hey, thank you for the talk. Your kappa parameter, it seems like it might be, tell me if this is silly or related or not, it seems it might be like in policy gradient methods, we often have an eligibility trace for the actor, which gives us a multi-step parameter for control. So is that related? So
actually we discussed about it in the paper, that the kappa parameter is really closely related to some other algorithm by John Schulman, I think, the JAE algorithm. Basically, the kappa policy iteration algorithm, you can think about it as the planning algorithm, which corresponds to JAE, at least that's what we think. Yeah, so that's my answer for that. It is closely related, yeah.
So in the problem that you used to evaluate this approach, did you try increasing the variance in the rewards, and did you try to see if using a longer horizon in the policy improvement stage led to degradation? Did you do any experiments by trying to increase the variance in the rewards?
Yeah, so I try to emphasize it. The results that I've shown are in the simple planning context, meaning that I'm not doing any sort of learning here.
Okay.
I have the model and I just perform the algorithm as is written here. Okay. Yeah, it's important to emphasize it.
Any other questions? Okay, let's thank the speaker.
Thank you.
So the next presentation is policy and value transfer in lifelong reinforcement learning, and the presenter is David Abel.
Awesome. Can you all hear me okay? In the back? Perfect. Great. So I'm Dave. I'm a PhD candidate at Brown. This is joint work with my collaborators Eugenai, Yue Guo, George Konadaris, and my advisor, Michael Lippman. So big picture, the goal of this work is to help understand this classic problem of an agent interacting with a bunch of problems and then using knowledge acquired from those problems to help solve some relatively similar problem. In particular, the perspective we take in this work is to establish some simple theory that can help explain near-optimal transfer in this restricted setting for two kinds of knowledge, both policies and values. The particular setting we focus on is that of lifelong reinforcement learning, where we suppose we have a fixed distribution D over possible MDPs. In particular, we suppose that the state action space of all MDPs in this distribution are fixed, as well as gamma. That means when we sample from this distribution, we're going to get a reward function and transition function. Then we give the resulting MDP to some agent to interact with for some number of steps, and then we repeat this process for the rest of the agent's lifetime. So over the course of the agent's life, it has to interact with and hopefully solve a bunch of related problems drawn from the distribution. As I said, we're focusing on a restricted version of this case in which first, just the reward function is allowed to change, and we fix the transition dynamics. And then second, we assume that all MDPs in this distribution are going to be goal-based MDPs. That is, we suppose there's some predicate on states that picks out which states are goal states, where you get some positive reward when you transition into the state, and those states are terminal. So in both of these cases, of course, there's intimate connections here to meta-learning, multitask learning, transfer learning, whatever you want to call it. We're going to just take a stab at establishing some of this simple theory, like I said. So the first objective we focus on is that of the jumpstart policy, which is in effect what exploration looks like when you have a bunch of different tasks to solve. So of course, exploration was one of the foundational challenges of reinforcement learning. Here's this little chicken from Freeway from the Atari domain trying to cross this road using random exploration. And as far as I know, this takes on the order of millions and millions of time steps before it gets even a single positive reward. The premise in the lifelong setting is that we can use exploratory experience in our earlier tasks to help guide our exploration in future tasks. So we formalized this problem with the following objective. We're going to try and identify the single jumpstart policy that's going to maximize our expected performance in expectation over this distribution. We here suppose a fixed start state, but of course you could just roll that into a start state distribution and push that into the expectation. We consider three policy classes of increasing complexity, the first of which are deterministic policies pi-d, classic mapping from states to actions. The second policy class are the stochastic policies, so mapping from states to a distribution over actions. And in the third case, the full-blown belief space class, which contains mappings from states and a belief distribution over which MDP you're in to actions. As I said, we consider two different cases for this distribution class. In the first case, the reward is allowed to change across the distribution, and in the second case, the MDPs have to be goal-based, as I mentioned. We're of course interested in the full case where the MDP can change arbitrarily, and we're sort of punting on that one for future work. We have some preliminary results, but nothing concrete. So our first set of results summarizes the nature of these optimal jumpstart policies in each of these different distributions for all of these policy classes. We build heavily here on the earlier work of Ramachandran and Amir, Singh et al. In 93, and Astrom in 95. I don't have time to go into the details here, but we also proved some value loss results that show how suboptimal each of these algorithms can be when they're applied in a setting in which they're not supposed to be applied. So for more on that, come chat with us at the poster or take a look at the paper. We then use these policies we identify for this first objective to help identify methods for exploration for PAC-MDP learning algorithms in this lifelong setting. In particular, we're going to inject these policies into value initializations as a way to seed exploration. So the PAC-MDP algorithms are so called because they're inspired by PAC learning, probably approximately correct learning. In particular, we track the amount of mistake steps that an agent's going to make over the course of its lifetime. A mistake is a case where, given an epsilon, the agent's policy is said to be epsilon below the true value function. So as the agent takes an action, if its policy is below this threshold, then we count it as a mistake. It's a time step for which the agent makes this mistake. PAC-MDP algorithms are those that have a bound on the number of time steps for which they will be making these mistakes with their policy. In particular, this bound must be polynomial in the size of the usual parameters, things like the size of the state space, action space, 1 over epsilon, and so on. And because it's PAC, that P says we need to have with high probability up at the top. So one symptom of a lot of these mistake bounds, these time step bounds, is the amount of over-optimism in your initial value function for these PAC-MDP algorithms, things like delayed Q-learning, as well as RMaths. So this effectively says the more over-optimistic you are, the more time you're going to waste exploring the environment. At the same time, you don't want to be too pessimistic because a lot of these algorithms explore using the principle of optimism under uncertainty. And so as a result, there's this delicate balance between over-optimism and pessimism. You want to sit somewhere right in the middle. So inspired by the work of Rao and Weitzen, who introduced Vmax that focuses on this notion of tempered optimism that balances between these two things, we introduced this algorithm MaxQ_init, which focuses on how to best temper your optimism in doing exploration and lifelong reinforcement learning. In particular, MaxQ_init says we're going to sample m MDPs from this distribution. We're going to run our PAC-MDP algorithm to get a Q-hat estimate. And MaxQ_init is dead simple. It's one line, well, really two. It says, after m samples, you're going to initialize your Q function for whatever learning algorithm you're using the max over all of your different Q values you've solved, your approximate Q values, on these first m tasks. The main result we prove here says, for m sufficiently large, this algorithm will preserve the PAC-MDP property with high probability while simultaneously reducing that over-optimism, thereby reducing your sample complexity. We run some really simple experiments in typical grid worlds. In this case, these are lifelong grid worlds, a slight twist. So the goals are all pushed to the top right of this grid world on the left. The agent starts at the bottom left and interacts with this problem for a little bit, and then gets to sample a new goal and try and interact with this problem. So our results are shown on the right. The x-axis is time, number of episodes, and the y-axis is the average reward. MaxQ_init is shown in green, with the beige being the traditional Vmax optimism. So as you can see, MaxQ_init improves over Vmax, and those blue and pink lines are theoretical optimums that we can't hope to beat, but we do see that MaxQ_init does approach them. We try a slightly different task distribution with higher entropy in the goal location. In this case, we see much higher variance in all of these approaches, which is of course to be expected since we're sampling and averaging performance over this distribution. But again, we find that MaxQ_init outperforms Vmax. We have a lot more experiments in the paper. These are just some simple explanatory ones, so I encourage you to check them out. So to summarize, we first tackle the nature of these optimal jumpstart policies to get a handle on what it looks like to do effective exploration in the lifelong RL setting. We then use these policies to inspire value shaping for the same purpose. In particular, we introduce this new algorithm MaxQ_init to do value initialization in lifelong RL that simultaneously preserves the PAC property while minimizing sample complexity. In the future, we're hoping to extend this analysis to finding which options can help lifelong RL by extending our analysis on one policy to n option policies. Come see us at poster 173. Thank you.
Questions? Okay, let's thank the speaker. Oh, sorry. Go ahead. Go ahead.
Is there anything in your method that requires goal state rewards, or could this generalize to any type of reward distribution?
Right, so in terms of the MaxQ_init or the jumpstart policies?
Either.
Yeah, so in the first case, it's we're looking at those distributions independently, and so different solutions are applied to either when just the rewards change or just goals change. MaxQ_init is supposed to work with either. Yeah, absolutely. Thanks.
Any other questions? So let's thank the speaker and move to the last presentation. So the next presentation is importance-weighted transfer of samples in reinforcement learning, and the presenter is Andrea Trinzoni.
All right. Hello, everyone. I'm Andrea Tirinzoni from Politecnico di Milano, and I will present a joint work with INRIA on the transfer of experience samples in reinforcement learning. Now, to begin with, let's provide an example motivating why we need transfer learning in practice. This is a real-world domain that was faced by our group a few years ago, and the goal here is to learn how to optimally control a water reservoir system. So in particular, what we want to do is to learn what is the optimal amount of water we should release from the reservoir every day. Now, because of how this problem is defined, collecting one sample, so verifying the effect of an action, naturally requires one full day in the real world, which makes the problem impractical to be solved using standard reinforcement learning technique, at least not in simulation. Now, however, it is very reasonable to assume that lots of historical data is available, which might come from very different reservoirs. Our solution will be to take all this data and transfer it to speed up the learning process in a new reservoir. So in particular, in this work, we consider the transfer of experience samples. So we assume to have a set of source tasks modeled as Markov decision processes, where we assume a shared state action space, but arbitrarily different rewards and transition models. Now, we consider batch reinforcement learning settings in which we are given a data set of samples from each source task, where a sample in reinforcement learning is defined as a tuple of state, action, the next state, and the reward. And our goal is to find out how to best transfer these samples so that we speed up the learning process in the target task. Now, there are several key advantages of transferring samples over other kinds of knowledge, which are worth mentioning here. Probably the most important is that a sample is completely decoupled from the learning algorithm. Even better, under our common state space assumption, the sample is not even part of the agent, it's part of the environment, which favors transfers between algorithm and agents. Second, typically in the transfer of samples, we do not require the source task to be solved, which is an assumption that has been made by many previous works. And finally, the samples themselves can come from any distribution, so it can be any policy. They can even be not in trajectory form, it can just be state action pair sample from some distribution, which is arbitrary. Now, what most previous works have focused on is to select the best source samples from each source task to transfer to the target task. And the main intuition on how this is done is that we are willing to introduce some bias in the learning process of the target task, but we expect to have a much larger reduction in the variance. The only problem is that this is definitely a non-trivial task to do, and if the algorithm for some reason fails, then what I mean, the bias which we introduce is larger than the variance we reduce, then we have negative transfer. The learning performance will be even worse than without transfer, and this is something we have to avoid in practice. What we propose to do instead is to define a method that transfers all the given samples, but to weight their contribution to the learning process of the target task based on how they are important for learning the target task itself. As we shall see, this has the main benefit of potentially reducing the variance while being ideally unbiased. And this makes our approach potentially very robust to negative transfer. Now, we based our method on the well-known fitted queue iteration algorithm, which iteratively fits the queue function by minimizing a loss with respect to the application of the empirical Bellman operator to our previous estimate of the queue function. Our main intuition is that when the data set of samples, here D, which is used to approximate the loss, is composed of samples from very different tasks, then we have sample selection bias. And our solution will be to use importance weighting to correct for the distribution shift introduced by the different tasks. So in particular, we call our algorithm importance-weighted fitted queue iteration. It's just a variant of FQI. And the main idea is to decouple the rewards and the transitions so that we maximize the amount of information we transfer in practice. Now, to do this, we start by fitting the reward function by using all the given samples. By noticing that at this part we don't need the transition samples, we are allowed to reweight the loss only by the ratio of the reward distribution in the target task, R0, and the corresponding distribution in the source task that generated that particular sample. Then we take this estimate of the reward function, we plug it into our empirical Bellman operator so instead of the reward samples. And finally, we use this modified operator to iteratively fit the queue function in the FQI fashion. Now, by noticing that now we completely remove the dependence on the reward samples, we are allowed to reweight every term of this loss by only the ratio between the transition distributions. What I want to point out here is that the key advantage of this decoupling between rewards and transitions is that we are able to transfer even when the source tasks have completely different transitions or rewards than the target task, provided that the other component is similar. While previous approaches focused on basically transferring all the experience samples, so the 4 tuple, jointly. One final remark is that in practice, we don't know the models, typically, so weights cannot be computed in closed form and have to be estimated. In the paper, we proposed an approach based on Gaussian processes where we're kind of trying to figure out what is the distribution of the importance weights. Unfortunately, due to time constraints, I won't be able to go into many details here about this one, but you can check the paper for this one. Now, before we made this comment about bias and variance, so let's see how it works theoretically. So in order to do that, we extended existing theoretical results for approximate value iteration algorithms to provide a bound on the distance between the optimal value function of the target task and the value function of the greedy policy returned by our algorithm at any iteration of our choice. What we found is that there are 4 main error terms constituting our bounds: the usual approximation error due to limited functional spaces, an estimation error due to finite samples, a bias due to the fact that we have to estimate the importance weight and we don't have access to the ideal ones, and finally the error propagation through iterations. So the key property here is that the bias in our bounds does not depend anymore on the difference between tasks, as in previous work. What we were able to do is to shift this dependence to the estimation error, which now does not depend anymore on the total number of samples, so we're not reducing the variance that much, but it depends on the effective number of samples we are transferring to the target task. Now, moving to some experimental evaluation, we consider different domains. The first one is a variant of the well-known paddleword, in which we consider transferring from 3 source tasks to 1 target task, where we just move the positions of the paddles. We consider 2 versions of the environments, one in which we fixed the dynamics between tasks, so only the rewards changed, and the second one where we allowed both components to change. So what we found is that our approach was able, in both cases, to achieve a very nice jump start, to converge very quickly to the optimal performance, but most importantly, to achieve better performance than several baselines we compared with, especially an approach to select the best source samples to transfer, which is what we wanted to prove. Finally, let's move back to the domain we mentioned at the beginning of the presentation. So the first thing we did here was to run FQI, plain FQI, no transfer, on a simulated and simplified version of the environment. And what we found is that FQI alone took roughly 200,000 samples to converge to the optimal policy. Fine in simulation, not so fine in the real world, since that's basically 500 years. On a transfer scenario, on the other hand, our approach was able to rather quickly converge to very good performance. But most importantly, it was able to immediately outperform both the approach for sample selection and the human expert. So to conclude, what we did here was to present importance-weighted FITQ iteration. That's a new approach for transferring all samples we are given and using importance weighting to correct for the distribution shift introduced by the transfer. We said one of the main properties here is that we are able to decouple rewards and transitions. We believe this is very important in practice if we want to maximize the amount of information that is transferred. Finally, we both theoretically and empirically analyzed our approach, showing its benefits over existing methods. And this concludes my presentation. Our code is available online, by the way, if you want to play with it. And if you're interested in knowing more, please come to our poster later. Thank you.
Any questions? OK, so let's thank the speaker. And this is the end of reinforcement learning session number 11. But we immediately start the reinforcement learning session number 12. So the last 3 speakers of this session we have 1 long talk and 4 short talks. The last 3 speakers of this session, can you please come forward? Because we haven't checked your laptop. We want to make sure that we change the laptops quickly. Come and connect. Come and connect. update for cooperative inverse reinforcement learning. And we have two presenters, Dhruv Malik and Malayandi Palanyapan. So we are listening.
Hello, everyone. Can you hear me okay at the back? Great. Hello, everyone. My name's Andy, and this is Dhruv, and today we're here to talk to you about some recent work we've done together with Jaime Fisak, Dylan Hatfield-Manel, Stuart Russell, and Anka Dragan. So let's consider a setting where we have a human and an assistive robot who wants to help the human achieve her goal. Now, the human wants to achieve something, let's just call it A. In an ideal world, the human would just tell the robot, I want A, and the robot would be able to figure that out, and they would go about trying to optimize this goal together. But that's not how it works, and we all know that. What really happens is the human must communicate her desire to some system designer, which could be herself, and the system designer must then design a reward function which is passed on to the robot, and the robot would then optimize this reward function by maximizing the sum of discounted rewards. Now, in all of that, though, it's not clear that what the robot ends up doing at the end is really what the human wanted, is really that A that the human wanted at the start. So the question we're going to be talking about today is how can we ensure that robots operate with the correct objective of their human designers, their true desired objectives. Now, let's talk about a quick example here. This is a simple collaborative cooking task where a human wants to prepare one of two recipes, and at each time step will prepare one of the ingredients you see on the screen. In the specific case, the human wants to prepare recipe A. And the robot wants to help the human prepare the recipe, but does not know which recipe the human wants to prepare. Now, you might ask, why can't the human just tell the robot what her true recipe is? And in the setting, I would agree with you, the human could just do that. But in more complex settings, for example, in self-driving, it's not clear that a human can explicitly tell the robot what he or she wants, maybe because they don't know it themselves, or they just physically can't write a reward function for it. For example, in autonomous driving, what does it mean for a car to be comfortable? It's not particularly clear. So to retain the core of the problem without sacrificing the simplicity of our explanatory example, we're going to assume the human cannot tell the robot explicitly what recipe she wants. Now, how would we go about solving this problem? One obvious approach is inverse reinforcement learning. In inverse reinforcement learning, the robot would simply observe the human perform the task, infer what the human's reward is, and then go about optimizing for that reward function. There are two key issues with inverse reinforcement learning. Firstly, it's a fundamentally turn-taking paradigm. The human would have to perform the entire task, the robot observes it, and then the robot goes about optimizing it. This is somewhat inefficient. There are ways to relax this, however, and it's a second issue that's a little bit more problematic. In inverse reinforcement learning, the human is assumed to be a demonstrator, i.e. they accomplish the task efficiently. What that really means is the human is uninterested in what the robot does or learns. The human's sole goal is to achieve the task. The robot is there also assumed to be a passive learner. The robot cannot interact with the human and can only simply observe the human. Now, the challenge with this is that there is a large body of literature that's come out recently showing that simply performing a task is not the best way to communicate what you want done. Showing is often better than simply doing. And so this is the problem with IRL. And let's look at what this means in the context of our example earlier. Now, once again, we're back in the example, and let's just say in this setting, the robot goes first and the human behaves as a demonstrator. So the robot would simply prepare the meat recipe, which is common to both recipes here. And the human, in this setting, in a next step, would prepare either the meat or the tomatoes because she wants to prepare recipe A. Now, since the human does not care about what the robot's learning, the human's ambivalent between the two and will prepare either with equal probability. In other words, the probability 1/2, the human would prepare the tomatoes. But the problem with this is the humans actually communicated zero information to the robot by preparing tomatoes here. The better way of going about this would be for the human to simply prepare the meat every single time, because by doing so, she is uniquely identifying what the recipe is to the robot. In other words, if by doing so, the human would be communicating to the robot through her actions. And IRL does not allow us to model this, which is something we expect and we need to do in real online collaborative settings. So we're going to look at a framework that relaxes these troubles with IRL called Cooperative Inverse Reinforcement Learning, CIRL for short. In Cyril, there are two key things in Cyril that make it slightly better in that, number one, the human and robot are modeled as jointly optimizing the human's reward function. What this translates to is that the human, the reward is incentivized, the robot is incentivized to maximize reward for the human. And secondly, the robot does not know a priori what the human's true reward function is. This incentivizes the robot to learn what the human really wants, and at the same time, it incentivizes the human to help teach the robot to maximize long-term gain, because the human will recognize that the robot's helping her maximize this goal. Formally, we define a Cyril game to be this tuple, where S denotes your set of states, which we assume to be fully observable for tractability reasons. We will get to that in a second. AH and AR corresponds to your human and robot actions. T is your transition distribution, as you might expect. And importantly, R is your reward function, which importantly is parameterized by the set of possible reward parameters theta. Now, the human will know what the true reward parameter in the problem is. The robot will not. And that is what makes it a little bit different. And the robot will instead hold the belief over the true reward parameter. Generally speaking, we model the robot's belief to be uniform at the start of the problem. Now, in the solution to Cyril, what we really want is the optimal robot policy. What's the best way for the robot to perform in this setting? So what we would do is we just go about maximizing the expected sum of discounted rewards. But the challenge here is the robot's policy necessarily depends on how the human behaves due to the interactivity of the problem. So what we're really going to do is we're going to maximize over both the human and the robot policy to arrive at an optimal policy pair. In other words, we're going to find the robot policy that best works with the optimal human policy. And we can think of this as an optimal learning policy for the robot and optimal teaching policy for the human. Now, I'm sure you might ask, we can't tell the human exactly what to do. And we agree with that, and we're going to get to that later on in the presentation as to how this is practically implemented. Now, we're going to very quickly walk through the definitions of Cyril in the context of our example earlier. Now, the state will simply correspond to how much of each ingredient is prepared so far already. The human's actions are just, you can prepare any ingredient or wait. The same goes for the robot. The reward parameters are just what possible things could the human have wanted. Could have wanted either recipe, and the reward function, as you see here, is parameterized by that reward parameter. It just says you get a reward of 1 if you achieve the correct recipe, and a reward of 0 otherwise. And of course, the robot will hold an initial belief over this. Now, a Cyril game falls into the class of what we call DEC POMDPs, decentralized POMDPs. For those of you familiar with decentralized POMDPs, you know that they're hard to solve. And for those of you not familiar with it, all you need to know is that they're really hard to solve. They fall in the class of problems that are NEXP complete. So they're actually very challenging to solve. Thankfully, there is some prior work that has reduced the complexity and, in fact, reduced the problem to be a POMDP, which is simpler but not quite yet perfect. Now, the key step in the POMDP reduction is, in fact, where it comes down to where you convert the local planning problem into a centralized planning problem. In other words, instead of it being a multi-agent problem, you can think of it as being a single centralized planner. What this means is instead of the human and robot locally optimizing and computing optimal policies, you have a centralized planner who computes the optimal policies of both the human and the robot, and these policies are handed down to be executed locally by both agents. The challenge here, though, is the human has private information. The human knows the true reward parameter that the robot and therefore the centralized planner do not know. Therefore, the centralized policy passed down to the human must cover all possible contingencies. In other words, the policy must be a mapping from all possible reward parameters to all possible human actions. So what this means is the actions in the POMDP are given by tuples. AR, which is just a robot action, and delta H, which is a human decision rule, a function mapping all possible reward parameters to human actions. And as you might expect, this makes the action space quite large and complex. In fact, it's exponential in the size of the possible reward parameters. Now, to give you an idea of how challenging this problem is, let's look at a very simple problem. A POMDP with 8 states, 3 human actions, 3 robot actions, and 4 possible rewards. We expect this to be somewhat straightforward to solve, but in fact, in over 4 hours of computation, we couldn't solve it on a simple MacBook Pro because the memory of 16 gigabytes was completely depleted, which you don't really expect to happen on such small problems. And the core issue was because the underlying POMDP had an action space of size 243, which is really quite large for a POMDP. Now you might say, let's try solving it with an approximate method like MCTS methods like POMCP. So we tried doing that too, and we found that you actually need a lot of samples to get even decent performance on such a simple problem. And as you might imagine, on complex problems, it's significantly worse. So now we're going to talk about how we ended up tackling some of these issues.
Okay, so before we get to our key insight, I wanted to kind of talk about what POMDP value iteration looks like. So let's kind of look at the search tree that's built when we're performing POMDP value iteration. So we can think of this as a Horizon 1 problem, but really this will generalize to any arbitrarily large POMDP, and you can just think of the images you'll see as just a single node in the POMDP search tree. So at the base of this Horizon 1 problem, we have all the decision rules of the human. And then right above that, we have the robot actions. And the goal of planning in exact value iteration in POMDPs is to find the optimal pairing between all the possible decision rules and all the possible robot actions, which gives you the maximum value. And right here, just in this Horizon 1 problem, you can see what the real difficulty is in solving this, because the branching factor is exponential in the cardinality of the reward parameter space. So if you look at the Bellman update, which regular POMDP value iteration solves, you need to solve this equation for all possible decision rules. And so what we kind of found was that in POMDP value iteration, in this special case of ours in Cyril, we have access to the Q values of the human, which lie at the base of the search tree. And again, in this Horizon 1 problem, if you unroll back the search tree, you find that the robot's Q value is exactly corresponding to the maximum Q value of the human. So in the image, you see that the action, which corresponds to the biggest Q value for the human, that action, which we've highlighted, is optimal. So we can get rid of all possible other decision rules and not have to plan over them at all. We only need to care about that one action that's optimal. And so we've gotten rid of the exponential branching factor that was causing computational complexity issues. And again, this was Horizon 1, but the fact that we have access to these Q values generalizes to any arbitrarily large POMDP if you unroll back the search tree. So let's compare the original Bellman update to our modified one. What we see is that the human, our Bellman update explicitly encodes the human policy. And in the standard case of Cyril, where we assume that the human is behaving optimally, that is just taking the human action which has the largest Q value. And then you can see that anywhere where we had decision rules, which was where the exponential blowup was occurring, we now just have human actions. And now the size of the action space in our POMDP is just the size of the number of robot actions. So some results that we had in our paper is that at each step of value iteration, not in the entire algorithm, but at each single step, you have an exponential reduction in complexity. And our modified Bellman update preserves optimality of the Cyril solution. So using the modification will not cause you to lose any value. And if you are interested in the proofs of these results, you can take a look at our paper. Another thing that is important to note is that we do not need to assume that the human is behaving optimally. This is why this speaks to how the Bellman update is general. Any behavior of the human, which is a function of our Q values, can be modeled by our Bellman update. So canonical examples of this in the literature include when the human is acting Boltzmann rationally or epsilon greedily with respect to Q values. Also, we can apply our modified Bellman update to a wide variety of POMDP algorithms. So we've already kind of talked about how we adapt exact value iteration. And most POMDP algorithms all use variants of the same Bellman update. So in our paper, we also chose to adapt point-based value iteration and POMCP. And we believe that most POMDP algorithms can be adapted by our Bellman update. We chose to adapt these specific ones in our paper because point-based value iteration and POMCP are the seminal algorithms for respectively solving POMDPs using point-based and Monte Carlo tree search methods. So, and also in our paper, we proved that these are modifications. Even with our modifications, these algorithms are asymptotically optimal. And you can, again, look at the paper for the proofs. So now let's take a look at the example that Andy gave earlier. And what you see here is, with a really simple problem, what took us 4 hours now only takes a fraction of a second. Or what we couldn't even solve in 4 hours now only takes a fraction of a second. And the reason is clear because we reduced the complexity, or reduced the number of actions from 243 to just 3. We see similar gains in the approximate solvers. So this is an example, this is the example plot that Andy showed with POMCP. And with our modification, we take far fewer samples. The number of samples is on a log scale. So, cool.
And very quickly, just to wrap up, we talked earlier about how we think there's some intuition for why Cyril should outperform IRL. In our simulated experiments, we do find that Cyril, in fact, does perform IRL. There's one final quick thing we want to talk about before wrapping up here today, which is there's a key question that remains. You know, Cyril is only really useful because we're assuming that people do behave pedagogically in these settings, that people do go out of their way to help teach robots and people they're helping to learn. So the question is, do people behave pedagogically? Because we've gone through all this work to learn this optimal policy for a teaching human, but if the human doesn't teach, this policy doesn't actually help them. Thankfully, there actually is a lot of work in the cognitive science literature that shows that in settings where the human is collaborating with a learner that has less information, the human explicitly goes out of their way to teach the learner. For example, they might pick suboptimal actions to help the learner recognize something quicker. Sorry, just one final thing. So to verify this ourselves, we ran a human subject study where the human was partnered up in a simple task with an AI agents trained with IRL and Cyril, and we actually found that this is a plot showing the proportion of times the human and AI agent team successfully accomplished the task, and of course you see they were much more successful with the Cyril robot than with the IRL robot. And when we asked the humans which robot they preferred working with the Cyril robot quite overwhelmingly, predominantly because some people said they felt better understood by the robot they were working with. And yeah, just wrapping up now. So today we talked about Cyril, which is a framework for ensuring robots act with their user intent objective. We talked about some recent work we did to derive a new Bellman update that generalizes the problem and reduces the complexity, making it possible to solve somewhat realistic problems. And finally, we looked a little bit into investigating optimal teaching and learning behavior. And with that, thank you very much. We're happy to take your questions now.
We have time for one question.
Thanks for the very excellent talk. So I was wondering, how can you, whether it's possible to extend this pruning idea to the sampling-based method, let's say the POMCP. Right now, I guess if I understand correctly, it's a modification for the value iteration algorithm, right?
Right, yeah. So actually, as we talked about earlier, so POMCP, the way that, you can think about POMCP solving being an approximation to the Bellman update. So as we talked about earlier on this slide, actually, we do apply it to POMCP as well. So we apply our Bellman update to value iteration, PBVI, and POMCP.
Oh, but have you shown it in the simulation results?
Yeah. So this is the number.
This is for the POMCP one?
Yes.
Okay.
This is for POMCP. So it works for pretty much all POMDP algorithms.
Yeah, I see. Great, thanks.
Thank you very much.
Let's thank the speaker. So the next presentation is fast Bellman updates for robust MDPs, and Marek Petrik is presenting.
Okay, thanks. Thanks everybody for coming. This is joint work with Clint Ho and Wolfram Wiesemann. So in many reinforcement learning domains, we really care about reliability. So for example, in medicine, we may not only want to minimize our costs, we want to make sure that the probability of hurting the patient is as small as possible. Now, there are many reasons why reinforcement learning could be unreliable. One of them, and perhaps one of the more important ones, is that the transition probabilities come from samples. They're estimated from data, which leads to errors. And as we've heard before, errors in reinforcement learning tend to compound. And so even if we have small errors in transition probabilities, this can lead to very large errors in policy quality, and then bad things can happen. So one elegant framework for addressing this problem is the robust Markov decision process. So this is a model that allows us to flexibly capture imprecise transition probabilities and compute policies that are immune to model errors. Now, robust MDPs are particularly nice because they preserve a lot of the nice properties of regular MDPs that we use in reinforcement learning. So for example, we can still use policy iteration, value iteration, and solving the optimal solution, and computing the optimal value function is polynomial time complexity. Unfortunately, they tend to be slow in practice. And our contribution is we developed new algorithms for some common classes of robust MDPs. So as I said, you can use value iteration to solve robust MDPs. And this is a simple illustration of the difference between a regular MDP and a robust MDP. So in a regular MDP, we assume that the transition probabilities are known exactly. And so the Bellman update simply chooses the best action with the expected value function. In robust MDPs, we relax this requirement of having a precise transition probability, but we replace it by a so-called ambiguity set and then compute an action which is best with respect to the worst case realization of the probability in this ambiguity set. So we're really playing a zero-sum game against nature where we're picking an action and nature is picking the worst plausible transition probability. There are many different types of robust MDPs. One way to classify the difference is looking at how the ambiguity set depends on actions. So the simplest model of robust MDP is known as state action rectangular, where we assume that the errors are independent across actions. Unfortunately, this model, while simple conceptually, often gives us solutions that are too conservative. And one way to address that is to look at a state rectangular model, which doesn't make this assumption of independent errors across actions. And so you can notice that here the constraint on the nature, on the ambiguity set, is shared across different actions. And in general, state rectangular MDPs can lead to much better solution than the state action rectangular MDPs. Another way of looking at the different robust MDPs is to look at the shape of the ambiguity set. In reinforcement learning, the most common way of using robust MDPs is to simply look at the L1 norm of the nominal point, P bar, and the nature. Now, this is an attractive approach because it's very simple. However, it's very limited because the shape of the ambiguity set is always the same. We only get to choose its size. And so one way to generalize this and capture more problem-related properties is to look at the weighted L1 norm. And these are two examples of the different shapes of the ambiguity set that you can get. All right, so we want to compute the Bellman update. This is more difficult than the regular update because we need to compute the worst case probability minimum P. As everybody can probably see, because L1 norms are polyhedral, we can just formulate this as a linear program. And so let's look at how well linear programs work. So if we have a small problem with 200 states, 200 action, this is a simple inventory management problem. we use Gurobi LP solver. The Bellman update on this problem takes 0.04 seconds. So it's very quick. Robust update is much slower. So for the simplest state action rectangular case, it takes 1.1 minutes. But if we look at more complex and more interesting cases, it may take up to 16 minutes to compute a single update. And I want to emphasize this is computing a single update for single state. So actually solving the full MDP takes weeks instead of minutes. This was recognized about 10 years ago. People proposed algorithms for the simplest case with an n log n complexity. Unfortunately, these algorithms don't generalize to the more interesting case of state rectangular MDPs and weighted L1 norms. So our contribution is this work is 2 new algorithms which can solve all of the 4 problems in pseudo-linear time, so n log n complexity. We do this by proposing a new homotopy continuation method for state action rectangular problems and combine this with a bisection and homotopy method for the S rectangular case. What I think is remarkable about the bisection approach is that we can compute randomized policies in combinatorial time using bisection. In terms of numerical complexity, we still get pretty good results. So we are able to reduce the numerical complexity of the state rectangular problem from 16 minutes to about 0.7 seconds. So this is about 1,000 times fold speed up. I would also want to say that while we are about 50 times slower than just the plain Bellman update, asymptotically, the methods are only log slower than a Bellman update. And so the difference doesn't really increase much with the problem size. So to summarize the contributions, we propose new fast methods for a wider variety of robust Bellman updates. We show that they have pseudo-linear time complexity. What's also important, what I didn't talk about, is that we compute also the primal solutions, unlike some previous methods that only compute duals, and so it can be used with policy iteration style methods. We ran a suite of empirical results, and we saw for moderately sized problems of up to 200 states, 500 to 40,000 times speed up over Gurobi linear program. And Gurobi LP solver is one of the best LP solvers out there. I would also want to say that while we look at the robust case, many of these computational methods are useful for model-based exploration in MDPs such as MBIE or UC-RL2. And please, if you want to learn more, come to our poster, number 87 in Hall B. Thank you.
Any questions? So I have a question. So is there any specific assumption under which this speed up is happening, if it's easy to take?
Good question. There's no specific assumption. We do have this structural coefficient K in the weighted L1 norm, but otherwise we make no assumptions and we get the exact solutions.
Any other questions? Okay, let's thank the speaker and move to the next talk. So the next presentation is decoupling gradient-like learning rules from representations, and Phil Thomas is presenting.
Okay, thanks. I'm happy to be here to talk about the paper Decoupling Gradient-Like Learning Rules from Representations, which was joint work with Christoph Dan at CMU and Emma Brunskill at Stanford. Okay, so because this is just a 10-minute talk, I split the presentation into 2 parts. The first is just the first single slide on its own, and that is targeted towards people who are already very familiar with natural gradient methods. The rest of the talk after that is essentially an ad for the poster, which is right after this, for anyone who's less familiar with natural gradient methods already. Okay, so for those of you familiar with natural gradient methods, what is this? Well, remember that Amari's work on natural gradients showed how you can take a gradient learning rule and convert it into a natural gradient learning rule. And this gives it some nice desirable properties, like the learning updates are typically covariant. What we did in this paper is we generalized his method to apply not just to gradient learning rules, but to a broader class, a class of gradient-like learning rules. And again, this results in some naturalized forms of the learning rules that have some nice properties, mainly covariant updates. Okay, so why is this important? This is important because a lot of the algorithms that we care about, like temporal difference learning or Q-learning or SARSA, aren't actually gradient algorithms. And so you can't directly apply Amari's natural gradient to them. Similarly, this goes actually for policy gradient algorithms. Since most policy gradient algorithms are missing a gamma to the t term, they're not true gradient methods, and so you would have to apply this generalized form of natural gradient to them. Also, this does go beyond just RL, and it could apply to optimization methods in general. So you can take this approach, this generalized form of natural gradients, and create a naturalized form of accelerated gradient methods, or a naturalized form of extra gradient methods. One thing I'd like to emphasize is that in this paper, we weren't trying to present a particular algorithm and sell it to you, to say you should use natural temporal difference learning. The goal was to say, how can you take your learning rule, whatever it may be, and convert it into a naturalized form that gives you covariant updates? In the process of doing this, we studied many of the covariance properties of these different methods, and we came across two interesting things, one that surprised me and one that really surprised me. The first was this. If you use estimates of the Fisher information matrix when performing natural gradients, you will still get covariant updates. Not approximately covariant updates, but truly covariant updates. Then the one that really surprised me is that even if you estimate the Fisher information matrix using data that came from the wrong distribution. So here's the Fisher information matrix for a distribution P parameterized by theta. If we estimate this by sampling X from a different distribution Q, and use that in natural gradients, we will still get covariant updates. So that really surprised me. There's a caveat. There are different strengths of covariant updates, and these can have lesser strength. More details on that at the poster. Next, we showed that no non-trivial second-order covariant updates exist. And, well, we showed that it's not likely that they exist. And you might be saying, wait, there's another paper here at ICML that gave higher-order covariant updates. These are not conflicting results. They're using a different definition of higher-order covariance. And lastly, we gave conditions under which these naturalized updates can be estimated in linear time. And so that means we're not estimating any matrices, we're not inverting any matrices. Okay, so on to the rest of the talk. For those of you not as familiar with natural gradients already, what is all this talk about covariant learning? I think the best way to describe it is with an example. So consider this. Consider that I give you n samples from some distribution, x1 to xn. And you want to try to guess what distribution they came from. You want to fit a distribution to it, and we'll assume you pick a normal. So you parameterize your normal distributions with the mean and the standard deviation. So your parameter vector theta is mu and sigma. You might then decide, okay, you'll search for the model that maximizes the log likelihood. So remember, the log likelihood is the log of the probability of your data given your model. And so we want to search for the model that maximizes this log likelihood term. And you might choose to do this using gradient descent with some fixed step size. This is like the go-to method for fitting a Gaussian to some data. Okay, so we also need to pick an initial point. So let's say that we start with the parameter vector theta1 is 2, 2. So mean 2, variance 4, standard deviation 2. What happens? Well, let's do this, and let's use 100,000 points, doing 100,000 steps of gradient ascent. And we're actually going to sample our points from the normal distribution with mean 3 and variance 9. This is what we get. We start down here in the left with the distribution with mean 2 and variance 4, and our gradient ascent updates to maximize log likelihood take us exactly where we'd want, towards the final destination of mean 3, variance 9, which is where the points were actually sampled from. This is great. Okay, here's the question. What if we parameterize normal distributions differently? What if instead of using mu and sigma, we used the mean and the variance? Would it behave the exact same way? We haven't really changed anything, right? We're still representing all normal distributions, just in a slightly different way. So you'd expect the algorithm to have the same behavior, but it doesn't. This yellowish curve is what happens when you use the mean and the variance. In general, if you use the mean and sigma to the k, you get wildly different behavior of your algorithm. Sometimes it converges quickly, other times it doesn't. So this is a case where performance has plateaued. It learned very quickly initially, plateaued at some performance level, and is slowly creeping towards the goal. So what's going on? What's going on is that gradient-like updates, which are updates that use the form, terms of this form, derivative of a distribution with respect to its parameters, or derivative of a function with respect to its parameters, make an implicit assumption. That assumption is that distances should be measured using Euclidean distance in the parameter space. So the distance between two normals is the distance between their parameterizations. And so this means that different parameterizations are resulting in a different notion of distance. This different notion of distance then changes the behavior of the algorithm, which is why we get these very different performances. So to put it differently, what's happening is our choice of representation is coupled with the learning rules behavior due to this implicit definition of distance. That is, when we choose our representation, when you choose mu sigma squared or mu sigma, you're implicitly choosing a notion of distance there. And that notion of distance changes what happens. It changes the learning rules behavior. So what is a covariant learning rule? A covariant learning rule is intuitively one where if you change the parameterization, it does not change the sequence of distributions that is produced. So that means we should get a curve that looks much more like this. Regardless of how you parameterize things, you get the exact same behavior out. And this is a plot from one of the covariant methods in the paper. So when does this happen in RL? This is the RL track, and so far I haven't really mentioned RL that much. So standard RL algorithms use terms like the derivative of your value function, your Q function, or your policy with respect to their parameters. These are making that implicit Euclidean assumption. Is this good? Is this bad? So what's happening is that, let's say we take the Q function and parameterize it by a neural network. We're making the implicit assumption that changing weights in different parts of that neural network are incurring the same distance, that changing a weight near the end of the network or at the start of the network have the same net impact on our Q function or our policy, which just isn't true. But this isn't just about deep neural networks. This also helps for flat problems. So in RL, this is also equivalent to saying that weights that are related to different states or state action pairs, changing them has the same impact on the policy or the Q function. This also isn't true. There's some state action pairs that we might see very often and others we might never see. So changing the weights related to those two have very different impacts. So how can we fix this? The fix to this is we want to let the user decide how to measure distance. So instead of you picking a representation, that implicitly defining a notion of distance that changes the behavior, you now pick your representation and you pick your notion of distance. And we will now give you the update that respects that notion as distance. So if you're trying to measure distances in policy space, you can choose something like KL divergence. If you're trying to measure distances between Q functions, you don't have to use the parameters of your neural network. You can choose your notion of distance in Q function space as something like the squared error, the squared change in the mean Q approximation. So what our paper is doing is it's showing how you can modify gradient-like updates, not just gradient updates, so TD algorithms as well, to use these user-defined notions of distance instead of that implicitly defined Euclidean distance. And I'd just like to wrap up by thanking my co-authors again, Emma Brunskill and Christoph Dan. Thanks.
Any questions? Okay, if there is no question, let's thank the speaker and move to the next talk. So the next presentation is called PIP's Flexible Model-Based Policy Search Robust to the Curse of Chaos. And Paavo Parmas is presenting.
Hello, I'm Paavo Parmas. I'm a PhD student at the Okinawa Institute of Science and Technology in Japan. This work grew out of my lab visits to Carl Rasmussen's lab at the University of Cambridge and to Jan Per's lab at the TU Darmstadt. The final co-author is my supervisor, Kenji Doya. In short, the work is about model-based policy search using differentiable models. However, in reality, the main contents are about gradient estimation, and I think it should be of interest to a wide range of researchers doing both deep learning as well as stochastic variational inference. Okay, so we were primarily motivated by an algorithm called PILCO. For those of you who are unfamiliar with this algorithm, I just want to show some performance on a cart pole swing up and balancing task on a real hardware. So Mark Dysonoff had previously done this task using the sensors in the apparatus. So this was my undergraduate project where I was trying to do this using a camera, and the idea was to see whether the algorithm can cope with noisy measurements from the camera. And as you can see, the algorithm solves this task in essentially just around 15 seconds of data. So it is incredibly data efficient. In fact, it is maybe so data efficient that there isn't even any reason to try to make it much better. Like if you cut 5 seconds off the data efficiency, it's not going to make any difference. So the question really is, how can we just scale this algorithm to larger, more complicated problems? And I think that this work makes a big step in this direction. Okay, so let me explain this model-based policy search framework from a more general perspective. So basically, it iterates these 3 steps. In the first step, it just applies the policy in the system and gathers some data. In the second step, so this second step is done offline. It trains a dynamics model on the data. So the dynamics model takes the current state as an input and the current action as an input and predicts the next state. Important that this is a probabilistic model, so it doesn't just make a point prediction, but it predicts a distribution over the next state. Then once one has such a model, it is possible to make trajectory predictions for arbitrary lengths. And because everything is differentiable, you can differentiate the cost with respect to the trajectories with respect to the policy, and just run a gradient descent procedure to optimize your policy. Now, this is a very general framework. A lot of people have done research on this. There's a vast literature. What differentiates Pilko is the special predictive framework which it uses. So let me explain this in a little bit more detail. So in general, if you want to predict the trajectory using a deterministic model, it's very simple. However, in Pilko, the input at one time step is the distribution from the previous time step. So now the prediction becomes an integral across this distribution. And in general, this prediction is intractable. However, Pilko makes an approximation where it estimates the output distribution as a Gaussian distribution. Now, while this is a strong point of Pilko, it is also a major restriction because this computation cannot be performed for arbitrary models. It cannot be performed for arbitrary policies. It really puts severe limitations on the algorithm and limits its scalability. And there is a simple idea which one can try to overcome this issue. So this is to use Monte Carlo particle predictions instead. And now other people have tried this idea and they haven't really got it to work. So in this work, we actually get this to work. And we also find out what the reason is why the previous ideas probably didn't work that well. So first of all, if you want to use particle predictions, you need to have some method of differentiating through the stochastic sampling operations. So the most natural way to do this is to use the reparameterization gradient. I won't explain this in full detail. The basic idea is that it is kind of like a backpropagation-like differentiation. And an important thing to note is that if the random number seed is fixed, then this gradient estimation becomes exact. This is also the method which previous researchers tried, and they couldn't get it to work. So here we find out why it didn't work, and I will explain this in the next few slides. Okay, so this slide looks completely fine. What I have done here is I have just plotted the objective function as a function of the policy parameters. So I picked a random direction in the policy parameter space and just started plotting what the function looks like. So this is the blue line. So this was averaged across the 1,000 particles, and there's a fixed random number seed. And there's also a confidence interval on this line, and actually a smooth line would fit within the error bars. So it seems feasible that it might be possible to optimize such an objective. However, now let's take a look at what the reparameterization gradient looks like for this line. Okay, so something has gone wrong here. So at the left-hand side, it is quite well estimated. But on the right-hand side, the gradient is just all over the place. And actually, the variance at the right-hand side is over 1,000,000 times larger than at the left-hand side. So even if you had millions of particles, you wouldn't be able to estimate a good gradient. So what is causing this? Actually, this is the exact gradient of the previous blue line, which I showed you. So this is quite strange. Okay, so what is causing this is just some kind of a numerical bug. So I did some more experiments to actually explain what was going on here. So let me explain the additional experiment I did. So what I do is I start from the start location, and I predict the distribution the second time step. And I put a grid on this distribution. This is at px1. And each grid point, I compute where the particle ends up going. I compute the cost for this particle, and I put this cost onto the grid. And then I just plot this. So this is a bit like the value function, except that it is for a fixed random number seed. So it corresponds to the value for a fixed particle. Okay, now let's see what this looks like for the left-hand side and the right-hand side. So at the left-hand side, this is quite a smooth function. So it is, and for the right-hand side, it's basically chaotic. It's a fractal-like pattern. Right, so basically the way the reparameterization gradient works is it tries to average samples on this value function computes the gradient and tries to average these together. And on the left-hand side, it's possible to find a good average. On the right-hand side, it's basically impossible. So it seems like it might not be possible to optimize the objective. However, all hope is not lost because actually there were also enormous error bars on the estimate which we had, so it is plausible that the true objective, if you were to average across an infinite amount of particles, would actually be a smooth function. If that were the case, if there were some kind of another gradient estimator which worked, it might be possible to still optimize the objective. Now, is there any other kind of gradient estimator which one could try? So another famous gradient estimator is the likelihood ratio gradient estimator. The nice thing about this is that it doesn't use the gradient of the function, so it's plausible that this would work. So usually people would use a stochastic policy and sample in the action space. In our case, we use a deterministic policy, and instead we sample with a stochastic model in the state space. So I haven't seen this before, so this is another a new part which we have done in our algorithm. And I've implemented this, and it works. So it is able to compute a good gradient also at the right-hand side. However, this is not ideal, as on the left-hand side, actually, the reparameterization gradient still had better performance. Is there some kind of a way to combine the best of both reparameterization and likelihood ratio gradients? The simplest idea which one could try would be to just take a convex combination of the two gradient estimators. And the optimal way to do this would be to just choose the weights proportional to the variance. But can we do better? Because actually we have a graph structure in our computation, so there might be some way to get a better performance. And indeed, this is possible. So I've invented this total propagation algorithm. Essentially, this is an alternative to backpropagation, which combines arbitrary gradient estimators during a backwards pass. And this works quite well. So actually, it achieves greater accuracy than the sum of the accuracies of the gradient estimators, which was combining, at least on these tasks. And also, the new model-based learning algorithm managed to match up to Pilko. Now, keep in mind that I'm only trying to match up. So this is a foundational work. The next step would be to swap out the model, swap out the policies, and try out bigger, more interesting, harder problems. Okay, so to conclude, I think that this work has shown some nice new insights into the exploding gradient problem. I think it is probably linked to issues which are seen in deep learning. And the algorithm is completely flexible. I hope that this will be used to create many new model-based policy search algorithms, as well as the total propagation could also be used for other applications. And I hope that it will be used a lot. Thank you. And also, my poster is number 8.
Any questions? Okay, let's thank the speaker. The last talk of the session and last talk of today is discovering and removing exogenous state variables and rewards for reinforcement learning, and Thomas Dietrich presenting.
Find the right dongle. Success. Okay, this is joint work with George Trimponius and Jitang Chen, who's here in the room, both at Huawei's Noah's Ark Lab in Hong Kong. So the problem that we are working on today really comes from the fact that often the natural way to express your reward function or your cost function turns out to depend on exogenous state variables or an exogenous subspace that your actions do not control. So let's consider, suppose I have the self-driving car of the future, and I want to train it to drive me to work every day by minimizing the total cost. So I'll formulate that as an MDP because, hey, this is an RL session. And the states will be the location of the car and some sense of the amount of traffic, some measure of the amount of traffic in the road network. So my actions will be what turns to take, and the cost function that's natural will be the total time to reach the office. However, if we think about that cost function, most of the cost is really determined by the behavior of other drivers and the amount of traffic, and I have very little control over this. So what can I do about that, or what are the consequences of that? Well, one is that if I look at the cost of my policy, it's going to have high variance, right? My return will have high variance day to day, trip to trip. And so this means I'm going to have to use smaller learning rates, larger sample sizes, and so on, depending on whether I'm doing policy gradient or Q-learning or what have you. But RL will be slower as a result of these exogenous variables which are injecting additional variation into my reward function. So why don't we try to formulate this as an exogenous state MDP? So what we do is assume or assert that the MDP state space can be decomposed into two subspaces, one of them exogenous, which we'll call X, and one endogenous, which we'll call E. And I want to emphasize that we don't assume that these are state variables that we're given. We're going to have to discover those subspaces. But it will obey this dynamic decision diagram, right, where the key thing is that neither are the current endogenous state nor the current action that we choose have any impact on the future state of the exogenous part of the state, right? So they're really, this is, it would be a normal MDP if there were an arrow from E to xt plus 1 and an arrow from A to xt plus 1. So it's the absence of those arrows and also the assumption of independence here that's the main difference. So with this change, we can now factor our transition state model. So this X and E would be the original state, right? We can factor it into an exogenous transition that depends on the full state and the action, and an endogenous transition, and an exogenous transition, which is just evolving on its own in a Markovian kind of way. Okay, now if we're willing to make an additional assumption, which is that the reward decomposes additively, then we can change the network to look like this. So we'll say that the reward function now is original reward function dependent on everything. It can be decomposed into an exogenous reward that depends only on the exogenous state and an endogenous reward that depends on everything. So with those two assumptions, it turns out it's quite straightforward to show that this exogenous MDP can be decomposed into a sum of an exogenous Markov reward process that's just evolving freely, that would be this thing here, and an endogenous MDP. So the value function for the full MDP is now the sum of a value function for the exogenous MRP and a value function for my endogenous MDP. And the Bellman equation is really the same, except that here we have now only the endogenous reward, right? This is the same transition function and so on. But it's the fact that we have removed these exogenous components of the reward that's going to help us. So a corollary of this is that any optimal policy for the endogenous MDP will be an optimal policy for the original MDP. So we should always solve the endogenous MDP, right? Well, not so fast. It turns out that it will be easier to solve the endogenous MDP if it really has lower variance in its returns. So it's possible that if the endogenous returns and the exogenous returns were negatively correlated, then they would actually be stabilizing each other. And so it is possible for that to happen. But in general, we don't observe that. So you can derive a covariance condition that says if the variance of the exogenous return, this is our notation for the random variable that is the return along a trajectory tau, if the variance of that is greater than minus twice the covariance between the endogenous and exogenous return, then we'll be better off solving the endogenous MDP. Okay, so now let's suppose that we suspect that we have exogenous variables in our MDP, and we would like to discover that exogenous state and remove the exogenous reward. Well, suppose we generate a database of transitions by running one or more exploration policies. And one thing we don't address in our work is what the sample complexity would be for this. But we'll assume we have a sufficient number of examples. And in the paper, we look at the general case. But for this presentation, let me just talk about the linear case, where we're going to assume that the exogenous state is a linear projection from the original full state space. So under that assumption, we get an additive decomposition. So this is the exogenous state here, and then the endogenous state can be obtained by subtracting the exogenous state from the original full state. So our goal now is to find a weight matrix that satisfies this conditional mutual information constraint, right? It says that the mutual information between the resulting state xt plus 1 and E and A at time t is 0 conditioned on xt. So kind of a messy thing, but that's really removes those two red arrows there. So in the paper, we described two algorithms for the case where we approximate the conditional mutual information by the partial correlation coefficient. That would be exact if everything's Gaussian and linear. Otherwise, it's an approximation. So we have to guess the dimensionality of the exogenous state. So we solve up to d dimension different optimization instances. These are optimizations on something called a Stiefel manifold. And we also have a stepwise algorithm. We do this with the MATLAB MANOPT procedure. So let me just show you two examples. There's a lot more in the paper. One is a toy problem. It's a linear dynamical system with 30 dimensions, of which 15 are exogenous and 15 are endogenous. And then they've been mixed by a linear mixing matrix. And so our challenge is to unmix them. We're using Q-learning with Boltzmann exploration. And so here are the results. On the vertical axis, so I'm plotting the endogenous reward. And for the first 1,000 steps of Q-learning, all the algorithms are learning on the total reward, the original MDP, while we collect our training data. Then at 1,000 steps, we apply the various algorithms for decomposing. And then we see that the red curve is our global algorithm, and it learns the best. The gray curve is actually so-called oracle. That's based on what we thought was the true endogenous state. And then the blue line is Q-learning continuing on the original full MDP. And what we see is that our decomposition algorithms learn much faster. And in fact, there was an additional exogenous state in the problem that we were not aware of. Then we also applied this to the original motivating problem, which was cellular network optimization. So you can control parameters of cell towers in order to try to minimize the number of users who are experiencing poor throughput. So we formulate this as an MDP. We have a sort of surrogate model for simulation. And here are the results. So the 0 line here is the default policy that is what Huawei recommends their customers use. And then what we see is that if we apply Q-learning, first we do 100 steps, which aren't shown here, to get our training data, do the decomposition, and then we see that our decomposition algorithm is able to achieve a 60% improvement over the baseline after about 160 steps, whereas the Q-learning on the full MDP takes about 260 steps. So we get quite a nice speed up here. And of course, we now want to extend this to looking at varying many more parameters in the cell towers so that we can deliver more value. So the summary is exogenous state can lead to high variance rewards, which can make reinforcement learning slow. An MDP with exogenous state and additively decomposing rewards can be decomposed into an exogenous MRP and an endogenous MDP. And solving the endogenous MDP gives us an optimal policy for the original problem. Thanks to Huawei for their support, and I'll answer questions.
Any question?
Maybe I'm going to get a Rich Sutton.
Rich has a question.
Rich is going to tell me he already did this.
No?
No?
No. The magic seems to be, it was really interesting, but the magic is how you find which variables are endogenous and exogenous. And I guess you're doing that by finding the mutual information between things. And so you're collecting sort of a large matrix, or a matrix, depending on how big the variables were.
Yeah, I mean, most of these problems were in the range of, tens of variables, so not massive numbers of state variables.
So you run for a pre-processing period where you figure out which are which.
Right. I mean, I think what makes these particular problems kind of accessible is that we get reward essentially at every time step. So we don't have a big delayed reward problem. We don't think it's strictly a bandit problem, but in these linear dynamical systems and in our cell tower thing, we're getting some reward at each time step, and I think that allows us to work on the problem. But still, You could have also have said, well, maybe I should just try to directly predict the reward. How much of the reward could I predict without looking at my actions? And, but if you had a problem with much sparser reward, that would be a much more difficult thing, whereas learning a transition model you get a training example every time step, and so that really pays off. So yeah, I guess that's the main point. Yeah.
So let me just ask, do you split it into the two phases, or could the two things be done simultaneously and overlapping?
I think they could be done simultaneously because we're not changing the representation that the reinforcement learning algorithm is seeing. We're just changing the reward function. And in fact, probably we should be monitoring that covariance condition and deciding whether to go back to keep the original representation or the original reward function or this specialized one. Because surely there will be problems where we're in one region of the space and then exploration leads us into a different part of the space where the exogeneity changes, and then we would want to track that. So, yeah.
Thank you, Tom.
Thanks for the talk. Very interesting. I just wonder the similarity with the credit assignment problem in multi-agent systems. So basically the difference here is that you assume that the other agents are stationary.
That's right.
But I wonder whether this could be extended to the more general case where the other agents are doing kind of the same thing.
That's a great question, and I don't know the answer at all. Yeah, yeah. And I'm sort of intimidated because I know there are like AMAS people in the room who maybe do know something more about that, and maybe you are one of them. I don't know.
No, really.
Okay.
I just wondered that it is very similar to that.
Right. So in some sense, we're assuming that all those other agents, like in our cell tower case, it's very similar to the driving case. When there are so many other agents that we can sort of treat them as an aggregate and not model them individually. But if we were in a problem where there was just like one other agent who was maybe adapting to us, then I think you'd want to explicitly try to model that other agent, really model the exogenous transitions instead of trying to just remove them, right? Yeah.
Thanks.
Okay, with this, we are at the end of this session. I would like to thank you all for attending this reinforcement learning session, and now you can go to the poster. Thank you, and thanks all the speakers for presentation.